Hi, I'm Paul Stubbs, Marketing Director for Autonomous Systems at Microsoft. Last year, we unveiled our Autonomous Systems platform, empowering engineers to apply state-of-the-art technology to their physical systems and processes, and showcasing some of the amazing things they had already created. Last month, we announced opening these capabilities for anyone to try with the preview launch of Microsoft Project Bonsai. What exactly do we mean by autonomous systems, and how does Project Bonsai help you realize them? Let's consider the evolution of automation, where we can see a steady progression from mechanized systems powered first by steam and then by electricity, which were controlled by manual operation, leading to increasing capability systems leveraging software to provide automated control for fixed operations, to today's systems which are increasingly leveraging AI to provide intelligent operation in highly dynamic environments. These systems include a wealth of scenarios across industrial robotics, motion control, machine tuning, and calibration, smart buildings and homes, process control and automation, and more. As we look across all of these, a few key common elements stand out. For existing control systems which are suboptimal, data-centric approaches are proving to not be enough to optimize them, rendering the majority of machine learning techniques insufficient. Rather, deep subject matter expertise and experience are the powerful ingredients that can be leveraged to create successful solutions. And all these systems must be able to be deployed and scale in the real physical world, bridging from the world of bits to the world of atoms. To realize these state-of-the-art autonomous systems, we are providing capabilities across 4 essential dimensions. First, a technique that can combine human and machine intelligence. First, we need to harness that deep subject matter expertise and experience. This is realized through a powerful technique called machine teaching. This is a fundamental and powerful shift in perspective. Instead of focusing on how something like the brain or a neural network works, we enable you to instead focus on what you are trying to teach and how best to teach it. This allows you to leverage your deep domain expertise to efficiently and effectively guide the acquisition of intelligence, just as you would for a new employee, in terms that are understandable to you and your colleagues instead of only data scientists or machine learning practitioners. You don't have to know your new team members' brains work to train them, but you do have to use your organization's hard-won knowledge and experience to teach them effectively. Machine teaching gives you the ability to do the same for machine learning. Second, simulation integration and scalability for training. For your system to safely and rapidly gain experience following your machine teaching programs, we bring together powerful professional simulation capabilities from the likes of MathWorks and AnyLogic with the massive scalability of Microsoft Azure, allowing your system to learn across hundreds or thousands of concurrent simultaneous instances running in the cloud. Automated generations and management, neural networks, and deep reinforcement learning algorithms is third. And we keep you focused on teaching these systems by abstracting away and automating the low-level mechanics associated with the underlying AI. When your machine teaching program compiles and runs, things like neural networks and reward functions are generated automatically on your behalf. And finally, a runtime to deploy and scale your models in the real world. And once you have built your controller, we provide the runtime capabilities needed to deploy and integrate it with the rest of your software stack. To help you get started on this journey, we have, in conjunction with our growing ecosystem of partners, created Project Moab, an open source machine teaching robotics hardware kit, which allows you to quickly learn via a fun desktop balancing platform. It can quickly go from seemingly straightforward, but in actuality decidedly non-trivial, to the exceedingly complex, all while enabling you to learn how to harness sophisticated simulation and machine teaching capabilities for your own use cases. In this demo, I will show you how to create an intelligent controller using Project Bonsai and Project Moab in simulation. Project Bonsai is Microsoft's machine teaching service to create and optimize intelligence for industrial control systems. Let's start by selecting Project Moab, an open source balancing robot to help engineers and developers learn how to build real-world autonomous control systems. The Bonsai project on the left shows the other projects we have created and simulators that we have connected. We can click on Add Simulator to choose one of the existing simulators, such as Simulink, AnyLogic, or Bring Your Own. In the center, we see the Inkling code. Inkling is a declarative, strongly typed programming language specifically designed for artificial intelligence. It abstracts away the vast world of dynamic AI algorithms that require expertise in machine learning and enables more developers to program AI. On the right is the concept graph. The graph has data from your environment or simulator called SimState. It has the concepts you are trying to teach the machine. And finally, the actions that the brain suggests back to your environment or simulator. Let's click Train to start training. The graph shows the number of simulator instances providing training data and the total iterations per second. We now have 20 instances running with 300 iterations. The goal chart shows the progress of our training. Based on our Inkling code, the brain is trying to achieve two goals: avoid falling off the plate and drive to the center of the plate. We're able to identify the average of the two sub-goals in the goal satisfaction. We can see a visualization of one of the simulation instances running. We can follow individual values going into the brain as the sim state and coming out of the brain as the sim actions for each iteration. We can select individual values that we want to watch in the graph below. We can even move the 3D model in the visualization to a position that lets us see what's happening. Now that we're satisfied with our simulation, we can go back up to the graph and wait for it to reach convergence at 100%. Now, depending on the complexity of your Inkling code and the number of states, the number of goals, and the number of actions, the time to reach 100% will vary. So here we can see at 14 minutes, we're getting closer. We're at 85% already. And now we're at 96% at about 22 minutes. And now we're at 99% at 24 minutes. And so this is pretty good. So 99.8 is a pretty good number to stop at. So simply click Stop Training to stop the training process. Once we stop training, we're able to export our brain and then use it on our edge device. Today, Project Bonsai supports a number of different architectures to export, such as x64 and ARM. Simply choose the processor and then click Export. Once you choose Export, you can either choose to delete the brain, or in a few moments the brain will be produced and you'll be able to see the output path and download it. We can now deploy our Docker container, which contains the brain and all the APIs, to our edge device, in this case the Moab unit. Now here in the Moab unit, we can do a number of options. We can set it into a manual mode, which allows you to control the device, but this tends to be very difficult. You can do it if you're holding the plate directly, but doing it through the joystick makes it difficult. So now we can switch into the mode that uses the brain that we just deployed to the device and see how it responds. And you can see, since our training was near 100%, that it does a pretty good job of really solidly putting the ball in the center of the spot. We can disturb it by pushing it to one side, and it does what we trained it to do, which is go right back to the center. We can also bounce the ball on the plate, and it's good enough to even grab it as it's bouncing on the plate, and we can see how the brain reacts to the ball being bounced or pushed or disturbed on the plate. So you can see it holds it pretty steady. There are little micro adjustments. We could try different things like, well, what happens if I have two balls to go onto it? And you can see that it tries to grab them, but it wasn't trained to handle multiple objects. So it doesn't do as good as if you just have one object. Now we can train the brain to handle other scenarios, and if we look to a brain that's been trained with obstacles, for example, in the way, we could say that the goal is to get to the center plate and to avoid an obstacle on the device itself, right? And this is a way that you can extend the brain functionality to not only achieve the goal of getting on the center plate, but you can add additional logic and functionality to the device. And we look forward to seeing the kind of things that you guys can create with this MOAB device in the future. Thank you for watching, and I would like to close with some ways to get started. First, get hands-on with the platform at aka.ms/as/preview. Learn with the Project MOAB Simulator and sign up to be amongst the first to get your own hardware kit at aka.ms/MOAB. And connect with us and each other and learn more with a wealth of materials at aka.ms/as.